Alright, we have a video here for the Thursday class, the 16th, I think. And you guys have just finished your quiz, and I hope that went well for everybody. I'll get those graded, and probably it'll be maybe Tuesday or Wednesday of next week before I get those up. But then I'll try to get them back to you on Tuesday. I can't guarantee that. If not, I'll definitely get them back to you by Thursday. Okay. So because we're running a little bit behind, we're going to jump right into Chapter 7. So Chapter 6 was really short, which is why we only had the quiz. But Chapter 7 is kind of like Chapter 5 in that it's got some really foundational stuff that we need to make sure we cover pretty in depth. So we're going to be in Chapter 7 for a good little while. It all hangs together pretty well, sort of thematically, but you do need to kind of really put your chemistry pants on for this. And those pants look sort of like this. Okay? Little feet. They're a little bit short, but they're still really, really cool. Okay? All right. So, all right, I hope you guys all brought those because that's what we need to put on today. All right, so let's dive right in here. Okay, I'll flip over to page 170 so you can follow along with what we got going on. So 7.1.1, don't really want to highlight anything other than how gross this all looks right here. And I hope to never see anything like that in my kitchen. You can ask Ada. Some of her icing might look like that for a little while, but hopefully not too often. So just the only thing I want to highlight here is the telltale signs of a chemical reaction. So we've got a release of heat and light, production of gas, such as carbon dioxide that fizzes out of a soft drink after the can has been opened, which ironically, I don't know that actually is a chemical reaction. It's just coming out of solution. I don't know whether that counts as a chemical reaction or not. So we'll have to think about that, and hopefully by the end of this chapter we'll be able to tell. All right, third's a color change. He points to this thing right here, that this is turned blue, and sometimes a precipitant may form. Okay, and that's so, kind of as we're going through these chapters, make sure you're noting these vocabulary words. So precipitation is rain, snow, hail, whatever comes out of the sky, it's precipitating down. Okay, and so often when you do chemical reactions, something forms and then sort of falls out of the solution or falls out of the liquid in a solid form, which is called a precipitate. Okay, any solid substance that forms when two solutions are combined. Okay, and so for something to become solid and come out of solution, that means it's not soluble, which means something that was soluble a second ago and now is not, means that there's probably a new substance formed there. Okay? All right. Moving on pretty quickly here. I want you guys to be really keep this in mind. I want to come back to this. I haven't had a chance to really think
whole lot about how to get this, but I feel like this is kind of an important concept here. This guy, Antoine Lavoisier, regarded as the father of modern chemistry, first to understand that combustion was a chemical reaction. That's awesome and important, but this is what I thought was really kind of piqued my interest. He was also responsible for helping turn chemistry from a descriptive science into a quantitative one. Okay? So what does that mean? It means that they're no longer just describing things. They're not saying, these goofy names and this is what the color change is. All right, we know that when tin is exposed to this, it forms the gray and it absorbs the life force and now it's green. That's just describing the color change. It's not trying to actually figure out what's going on other than saying something like this, absorbs life force or something like that. Okay, that's not fitting it into a comprehensive web of knowledge in which some things are explained by other things and they all kind of fit together. And so he noticed that tin turned to tin oxide when it combines with oxygen in air. And so he demonstrated that air is composed of more than one gas, then oxygen accounts for about 20% of it. So he figured out an actual number for the percentage of oxygen in the air. I don't know exactly how he did that. I assumed he has, he put exactly 1 gallon of air, and then he saw that exactly 20% of that, 1/5 of the gallon, was, combined into a substance, and they measured a pressure drop in the chamber. I don't know exactly, but so anyway, they kind of talked through here. I just don't understand exactly how that proved it conclusively. But right here is the important thing from 7.1.2. Law of conservation of mass in chemical reactions. In any chemical reaction, the total mass of the products equals the total mass of the reactants. Okay, so for us, that's seems pretty straightforward, but it only seems that way because you guys have been hearing that your whole lives. Conservation of energy, conservation of mass, conservation of this and that and the other. Okay, all those things took decades and decades and decades to get established as basically the laws of nature that are sort of fundamental principles that tell us about how the world works. Okay, so try not to take that kind of thing for granted. It kind of makes us the term I've heard is chronological snobbery, sort of thinking the people that live in our age are smarter than everybody that lived before. Lavoisier is smarter than any of us have ever thought about being, and he was brilliant. Newton was brilliant. Tons of these scientists were absolutely brilliant, and it just seems like they discovered these self-evident things, but that's not really the case because they weren't self-evident at the time. Okay, so the key takeaway here is that your mass products have the same mass or equal to the mass of the reactants. Okay? All right, so we'll circle back around to that as we get out. All right, so now I want you guys to be, again, just following along here as we go through this chapter, but I want to move my book out and I'm going to write things instead of just show you in the book so that we can go kind of step by step. All right, so let's write a couple of rules. Okay. We've got phases, and the clothes are now dry. The phases of matter. Okay, so that's gas, liquid, solid. There's also aqueous, AQ, to mean it's in solution.
are shown. And you guys can see that right there in above when we've got the 2HGO thing. It's a solid goes to a liquid and a gas. Okay? So let's just write all these out. And I've seen him often sort of below the line. He does not have that. But I have definitely seen that to be the case. Okay. All right, so let's go through and let's label kind of everything here. All right, so we've got the phase of matter. Okay. And we need to also note that this is the reactant side, and this is the product side. Okay. I tutor tons of people, and that seems to be something that's like basically confusing, and I don't really understand why it's confusing, because things that react is what you start out with, and they go to the products. So just let's go ahead and just know that, okay, because that will be asked at some point on a quiz or a test. What side is what, okay? And let's just, if you're confused about it, let me know, and I'll try to explain it a different way. But I think it's pretty self-evident. All right. So this is just an indication of the direction of it. Okay, now later on we will see that there are some things that as they establish equilibrium, they have an arrow on both sides, so it's kind of a double-headed arrow there, and that just means it's establishing an equilibrium between the two, and things are moving back and forth between one side and the other. Okay, and that's typically in solutions as acids and bases, or as we dissolve a certain amount of thing in a solvent. That's going back and forth. Okay, right now all we're talking about is a specific set of reactants moving to products. Okay, that is not, they're not going to get any more complicated than that right now. All right, so what does this mean? This means there is heat added. Okay, and I think he says right here a particular temperature. The temperature is written below the arrow, so we might see something like 250 degrees C. Okay. We talked a little bit about that, about steel, how above a certain temperature it does certain things. Lots of chemistry reactions are very temperature sensitive. I happen to brew beer sometimes, and it can dramatically affect the taste of the beer at the end of the deal. Whether it's been kept at like 55 or up at 70. A lot of reactions in your body are extremely temperature sensitive, which is primarily why you keep a 98.6 or thereabouts. Some people run a little hot or a little cool from there, but very close to, keeping a body within 1 degree or 2 degrees is a very difficult task. And a lot of your energy is spent every day doing exactly that. Okay, we can live comfortably within about 25 or 30 degrees, but we have to do a lot of stuff to keep our temperature outside of that range. We have to do a lot of stuff to keep our bodies in a very specific temperature state. Okay. And that's because a lot of the enzymes, and we haven't talked about those yet, or catalysts that are in your body only work at a very specific temperature. And forget about proteins denaturing or anything like that. Long before that happens, if you keep running a fever for a long time, certain enzymes just break down and they don't work anymore. So anyway, all I have to say, a lot of temperature-dependent stuff going on in chemistry. And of course, we're only scratching the surface in this class. And if you ever take a heavy-duty chemistry class in college, you'll get in to the temperature stuff a lot more. All right. So note that we've got these numbers, and we can think of these as the mole ratios. Okay. All right, you can also think of those as individual atoms or molecules, right? So if we had 2 molecules of HGO, okay, and I'm not going to do any Lewis diagram or anything of it, but I do want you to see it, all right? We would have 2 of these, okay, and then we would see that in this equation, okay, what's going to happen? We've got 2 HGs here, so we're just going to end up with an HG and an HG, okay, because they're not bound together. Bound together would be Hg2. Okay, that's not what we're saying. Okay, these are separate Hgs. And then we do have an O2 bound together like that. Okay, and again, that's not the right Lewis diagram or anything like that. I'm just showing up for conceptual purposes here. Okay. All right, now, what's important about this? Well, what's important is that we have 4 atoms, 2 HGs and 2 Os, and we have 4 atoms over here, 2 HGs and 2 Os. Matter is conserved. Okay. Now, this, of course, is identical to the situation if this is a mole ratio or an individual atom ratio. Okay. Again, if we think of the mole as analogous to the word dozen, if we had 2 dozen of these, we could draw 24 of these guys. We'd also have 2 dozen of those, so we'd have 24 O's. We'd have 2 dozen HGs over here, so 24 of those, and 1 dozen O2s, which would be, each one of them would be 2, so we would have 24 O's all told. Okay, matter is always conserved. All right, and he calls this the yields arrow, and that makes sense, of course, because one thing yields another, meaning that one thing becomes another. All right, or gives up another here. Let's see what else. Okay. All right. So we then are going to draw conclusions. Okay, and a better symbol. And I'm sorry, I said it two-headed arrow. It's actually kind of that, almost like a sideways electron filling deal. Right. So make sure you're noting those, because we're gonna use those right, and I am gonna ding you if you don't use those properly. Okay, because we're we're learning that grammar of chemistry. So just go ahead and get right with using the correct deal. Okay. So note right here, one other thing, we've got if there's something that's written over that arrow and it's a substance, that means that's a catalyst. Okay, and we're going to talk about those much more in depth. There's something that aids in a reaction but does not actually get consumed in that reaction. Okay, silver is often a catalyst. Platinum are catalysts. They aid the reactions without actually being eaten up themselves. Specific heats that are required is this one, like we said. Specific pressures can be. Okay, so this is all pretty intuitive. Is that special conditions go over the arrow? Okay, all right, so no problem. Balancing equations. All right, let's just go ahead and run through the rules. Okay, and then we're just gonna work through them. Okay, I think practicing them is going to be our best approach. All right. All right. Whoa, that looks kind of weird there. Sorry, at the edge of the counter. Okay. All right. All formulas for compounds must be correct with the correct subscripts. Okay. H2O cannot become H2O2 to balance an equation. Okay. You can only add stuff in front of them, so make sure that you don't change water into something else because you want your oxygens to balance. Okay. If this is, cyclooctosulfur, which is S8, and of course cyclo just means it's in a ring. Octo means there are 8 of them, so it's 8 sulfurs in a ring. Okay. You can't just change it to S7 to balance it, because that's not the compound. The compound is 8 of them bound together. Okay. Now, at some point it may become S7. That may be the chemical reaction, but you can't change those things to make the equation balance. Okay. The only thing you can do is add those things in the front. Okay. Go ahead and know these. Diatomic substances. H2, N2, O2, F2, Cl2, Br2, I2. Thankfully, they are not randomly strewn about the periodic table. Okay, we got H2, of course he's way over here. N2, O2, F2, Cl2, Br2, I2. Boom, boom. And if sometimes, like it's better to put the H over here, because sometimes it kind of acts like that. You can see it's just this, and then if H were there, coming on down. Okay. So set up a little alarm bell in your mind. If you see an H by itself, it better have a 2 under it because it does not form single deals. Okay. You will never find H by itself in a chemical equation. It's always H2. N2, O2, F, Cl, Br, I2. Okay? All right? I'm not going to expect you to know, super strong, the S8 and the P4. They're just not nearly as common. But O2 is going to show up all the time. Cl2 is going to show up all the time. H2 is going to show up all the time. So we definitely need to take note of that. All right? The equation must contain all the reactants and products that are parts of the reaction that actually occurs. Okay? So basically, you can't just say, oh, it forms a gas and that leaves, and so I don't need to show it. No, you need to show it because it gets formed. It just happens to be a gas which doesn't like to hang around. Okay, that as far as balancing the equation, that's not okay. You need to. Anything that happens with any of those atoms, you got to show them on both sides of the equation. Okay, and she just says it's the process of adding coefficients in front of either reactants, products, or both until the equation displays equal number of atoms of each element. He's got a couple of little tips here, but yeah, and so this is an important. I'm all over the place here, guys. Sorry. Usually treat polyatomic ions. All right. In formulas as single units. Okay, so like a carbonate or something like that. If you've got H2CO3, say. Okay. This guy is going to kind of move around as a package. Okay, so very often you'll see, let's say it was, that may be a bad one because often that breaks down to CO2. But let's say sodium nitrate. Okay. And you have something, something, something. Often you'll have a calcium nitrate over here. And so this guy's kind of moving around as a package. Okay, so all the same rules apply. You can count N's, you can count O's, you can count calciums, N's and O's and sodiums, and there have to be something else here to ever make it balance. But often it's easier to think of it just as one package of NO3. Okay, and you guys do it however you want. I think you can treat them as packages often, unless you don't see that as a unit on the other side. So if this goes to like H2O and CO2, well, obviously that polyatomic ion gets broken up, okay, into this. But we'll get into all that. All right. And then we have to, he says do more complicated stuff, but you guys will figure that out. When you finish balancing, make sure there are no common multiples. So if you've got like 2, 2, 4, and 2 as your multiples, as your coefficients, like right here. So here we got 2, 2, and 1, so we can't reduce that at all. But if this was 4, 4, and 2, we would say, whoops, we just multiplied by 2 too many, and so we would need to reduce everything, just like we reduce fractions to their lowest, lowest form, I guess is what it's called, simplest form, maybe. Anyway, you reduce them until you can't reduce them anymore. There's nothing you can do here to get those numbers down. All right, so let's just work through some of these examples, and I know you guys could read these, but I'm just gonna take the time and go through them. So let's just look at example 7.1 here, and I always remember in chemistry that we always seem to work the easy ones in class, and then when I got home, the homework was super hard, and I was like, man, you didn't cover this kind. So y'all let me know if I end up doing that to you, and I'm glad to work anything at any point for you guys. All right, let's get focused here, camera. And nope, I'm not going to focus. I'm going to make him focus. There we go. All right, first one. He just formula equation, so he's not. And as you're doing this, I don't necessarily think you need to keep track of the states of matter for balancing purposes. That's just extra stuff you got to write down, okay? But as you write the final equation, make sure you put them back in. All right, so let's just go what we've got. We've got zinc, we've got hydrogen, and we've got chlorine on both sides. Okay, and so I'm just gonna and we'll just tally them. What do we got? We got one on this side and one on that side. One here, one there. For hydrogen, we got one here. Two here. So that's not balanced. Then we got chlorine, one on this side and two on this side. All right, so all we got to do is go to whichever one we want to, and we put a coefficient that makes that one balance. Don't worry about doing everything all at once. Sometimes it works out and sometimes it doesn't. Just focus on one at a time and then move on to the next. Okay, so what do we got? We need to get 2 on this side, so we're just going to put a 2 in front of that. All right, and I keep up with the tallies. You don't have to even do tallies if you don't want to. This is a way for me to make sure that I am identifying properly which ones are not highlighted. Which ones are not balanced. All right, so that gives me 2 hydrogens on this side and 2 chlorines. Oh man, isn't that sweet? Just like that, it balances. Okay, so then we'd come back here and we'd do this. And balancing it never changes these states down here. You'll be told those, okay? Unless at some point we get to where we're trying to figure out solubilities or stuff like that. We're not trying to get into all of that right now, okay? Again, in a college course, you'd probably be asked to identify whether that was going to become a solid, because if it's not soluble in whatever solution you've got going on, it's going to become a solid precipitate here. And you might have to label those. We're not doing that. I'm just telling you that expectation exists out there for other classes. Okay, so that's it. That's balanced. Okay, that's about as easy as they come. Okay, you only need to put one number, boom, the whole thing is balanced. All right, let's look down at the next one here. Fe, 2, and again, they would tell you, unless they were asking you about it. I mean, we had to make some compounds like that. So if I told you, hey, this forms Fe2 parentheses oxide, or Fe3 parentheses oxide, all right, like this. You know, you can be asked and say, all right, iron and oxygen combine to form iron 3 oxide. Write a balanced equation for that. Okay? You would have to take that all the way from nothing to writing this. You might not be given this. You might not be told that this is diatomic. Okay, so those are all ways that you can be tested on these kinds of things. It's almost like a math problem, right? So you take the math problem, and they tell you Sally goes to the store and buys 300 dozen eggs. That's a lot of eggs, I know. And, you know, but they were 84 cents a piece. No one says multiply the number of eggs times 0.84. They're telling you to take it from a word problem into a math problem, which is kind of like what we're doing here. You could be given a narrative and have to turn that into a balanced equation. All right, so what's wrong? I've got Fe, I've got O, and I've got, and that's it. Okay, and what do I have? I've got 1 on this side, 2 on that side. Oxygen, I've got 2 on this side, and I've got 3 on this side. All right, let's just balance what we need to balance first. Okay, and he says go with a more complicated one. Offhand, and I'm actually just going to go left to right just to see how it works out. Okay, so let's put a 2 right here. Does that balance it? Oh, looking good. All right, so we got Fe2 on both sides. But now our oxygens are still not balanced. Well, what can we do with this? Well, what did we do when we were looking at those oxidation states or those charges, right? We knew that when there was a 2 and a 3, you had to get 2 of the 3 and 3 of the 2 to make them work out. Okay, so that's kind of the same thing we got to do here. Let's balance the oxygens. Let's put a 2 in front of him, and we'll go ahead and record that. So that gives us 4 irons and 6 oxygens. And now over here, we need to get to 6 oxygens, so we'll put a 3 in front of that, and that gives us 6 oxygens. Now everything's balanced. Wait, no, it's not. This is still not balanced, so we see that in fact that shouldn't be a 2, that should be a 4. All right, so our balanced equation is 4Fe plus 3O2 goes to 2Fe2O3. And we would put our solid, gas, solid. Okay? And I would say, you know, I think it's appropriate that we could put just an H2O has to be present as a catalyst for that. Dry iron does not rust. Wet iron really rusts. Okay? All right, so that's the basic concept there, and we've got to work. Let's see. I was going to see if working one more would be helpful. Well, we're probably short on time. Let's just leave it there. We'll work a couple more examples with these to make sure that everybody's clear on it. And we'll just pick that up on Tuesday as we move on through. Where else are we going? Very briefly, so you can know where we're headed. We've got oxidation. Tilt you guys a little bit to show you. Got oxidation states. Getting into losing and gaining of electrons and what that reduction versus oxidation, what that means. There's a lot that goes into all of that. Okay, so we'll talk through all that. No worries. General types of chemical reactions. There are. I always thought there were 5, and I think he actually adds one that I didn't really think was a separate deal. The activity series of metals. Some metals are much more reactive than others, and we know what happens when a more reactive metal gets in contact with a less one, and all that stuff. Super cool stuff there. We'll explain some weird phenomena in the world. Single replacement, that's types, combustion, double replacement, acid-base neutralization. Oh, that's the one I didn't think was one of the ones that was typically categorized with these, but it is redox reactions or oxidation reduction reactions, stoichiometry. Yeah, so we've got like at least 2 more classes to get through this chapter. Limiting reactants. Yeah, at least 2 classes. And I think once we get through this chapter, we'll be ready for another lab. Okay, so I'm working on that, and we will get that prepared. So we'll have a lab day soon. I think probably the best we're going to be able to manage is 2 more labs for this year. They're really a lot of work to get those together, and we don't have a great lab for those. So we'll probably do one about limiting reactant, and then I don't know what the last one will be. We'll just have to kind of see how that develops. So, all right, I'll get those quizzes back to you guys, and y'all have a good weekend. Make sure you look at your homework, get it done, read ahead, get familiar. This is pretty cool stuff, and this is really some of the good meat of chemistry that we're learning in this chapter. So put your chemistry pants on, and I will see you guys. There they are again, in case you forgot what they look like. And I will see you guys next week.